So once again, good afternoon, students. Today we are going to discuss about the instrumentation amplifiers. Okay. So instrumentation amplifier is basically a special type of differential amplifier, right? Where it has lot of advantages over the normal differential amplifier because the normal differential amplifier finds lot of limitations in terms of the input impedance, gain, and CMRR. Where in case of instrumentation amplifier, we have lot of advantages of very high input impedance, high gain, and high CMRR, that is common mode rejection ratio. So in this lecture, we'll see the fundamentals of instrumentation amplifier, its pin configuration, physical appearance, and its circuit diagram, and we'll be going to derive the derivation of the gain of the instrumentation amplifier, जो कि बहुत इंपॉर्टेंट है और आपके यूनिवर्सिटी एग्जाम में अक्सर पूछा जाता है. So first, instrumentation amplifiers are used where high accuracy and stability of the circuits are required, particularly some industrial application like biomedical applications in case of ECGs and EEG. Can anyone tell me what is the full form of ECGs and EEG? कोई बता सकता है आप में से? Yes.
इलेक्ट्रोकार्डियोग्राफी.
हाँ, ECG का फुल फॉर्म है इलेक्ट्रोकार्डियोग्राफी, whereas EEG is full form is having electroencephalography. ठीक है ना, ये आप देख लीजिएगा नेट पे एक बारी. And these instrumentation amplifier are also finds its application where long term stability is essential, particularly in automation sector. Okay, so these are some application aspect. Because in our first class, when we started the signal conditioning, we have said that the output of transducers is usually having a low voltage. So we need to amplify this signal before transmission and further processing. And operational amplifiers are mainly used for this purpose. So we can say that the operational amplifiers, or which are abbreviated as opamp, these are the integral part of any kind of signal conditioning systems. Okay, so we have said that the instrumentation amplifier is a type of differential amplifier. So first we'll discuss some basic fundamentals of the amplifier, then differential amplifier, normal differential amplifier, then we will switch our discussion on the instrumentation amplifier. Okay, so most of you have already studied about the operational amplifiers. It is the most popular op-amp is the 741 type IC. I think you already know. So it is basically a 8-pin configuration where we have two input terminals, 2 and 3. You can see that the number 2 is inverting input and number 3 is non-inverting input, right? And the pin number 6 is reserved for the output part. Okay, and pin number 4 and pin number 7, these are the supply for the operation of this ICC. So when you apply the input at inverting part, then our output will be having negative sign, and if you are apply the input at non-inverting input, then same sign output will be appear at the output side. So this is some fundamental so that you can recall it. If we talk about the differential amplifier, right? So differential amplifiers finds a lot of application in instrumentation. Okay, so this slides is basically showing you the circuit diagram of a typical differential amplifier where we are applying two inputs at both the terminals 2 and 3 at non-inverting terminal as well as at inverting terminal with some resistors. Okay, so T naught is the output which is proportional to the difference of these two inputs E1 and E2. Okay, so this is the expression of output voltage of a normal differential amplifier, and if we select this particular ratio, then the output voltage becomes R2 by R1 E2 minus E1, where E1 and E2 are the two inputs which are applied at particular nodes. Okay, so this is just for the recalling purpose, our main discussion will be on instrumentation amplifier, right? So यहाँ तक आप लोगों को ये समझ में आ रहा है कि हमारा जो नॉर्मल डिफरेंशियल एम्पलीफायर है उसका जो आउटपुट है वो प्रोपोर्शनल होगा डिफरेंस ऑफ टू इनपुट्स। ओके, ये चीज आप लोग ध्यान रखिएगा। इसके बहुत सारे ड्रॉबैक्स हैं, सो दैट्स व्हाई वी मेक यूज ऑफ इंस्ट्रूमेंटेशन एम्पलीफायर्स। तो सिंगल ओपैम्प आप लोगों ने देखा कि जो हमारा डिफरेंशियल एम्पलीफायर है वी आर यूजिंग ओनली सिंगल ओपैम्प, वन ओपैम्प। ओके, सो इट सफर्स फ्रॉम लिमिटेशन ऑफ फाइनाइट इनपुट इम्पीडेंस एंड मोर ओवर its gain is also limited because the gain bandwidth product is limited. So we, in order to overcome these drawbacks, we need an improved version of this amplifier, and this improved version of differential amplifier is known as instrumentation amplifier. Okay, so जिस तरह से आपके नॉर्मल ऑपरेशनल एम्पलीफायर की आईसी आती है 741 के नाम से, उसी तरह से आपके इंस्ट्रूमेंटेशन एम्पलीफायर की आईसी जो है वो AD620 के नाम से फेमस है। and this is the pin diagram and this is the physical appearance of this IC. Okay, so now come to the configuration of instrumentation amplifier. इसको आपको बहुत ढंग से समझना है। Actually an instrumentation amplifier basically consists of three op amps, right, and several resistors, whereas the normal differential amplifier is having only one op amp. Okay, and the whole circuit is divided into two stages. Okay, मैं आपको सर्किट डायग्राम दिखाऊंगा आगे। उसकी जो फर्स्ट स्टेज है उसको हम कहते हैं बफर सर्किट एंड द सेकेंड स्टेज इज नोन एज डिफरेंशियल सर्किट। सो दिस इज द मेन सर्किट डायग्राम of an instrumentation amplifier where you can see that there are three op-amps, op-amp 1, op-amp 2 and this is op-amp 3. Okay, and this there is a line which is separating the two stages. This side is basically the input stage and the differential side is known as the output stage. Okay, in the input stage we have two op-amps, op-amp 1 and op-amp 2, and these op-amps are having inbuilt buffer circuit, so there is no need for the separate impedance matching devices required in this case. Okay, and here you can see that in op-amp 1 and in op-amp 2 there are two input supplies which are applied on non-inverting terminals. V1 is the input of op-amp 1 which is applied at non-inverting terminal, and V2 is the input which is applied at the non-inverting terminal of op-amp 2. Okay, and there is a negative feedback of op-amp 1 as well as op-amp 2 with resistance R1 and R1, right? And in between these two resistances there is a resistance called RG. Sometimes this RG is also known as gain resistor, because in final conclusion when we derive the expression of this output voltage, or you can say the gain, then you will find that this RG plays a very important role, because when we change this RG then only we can get the variation in the CMRR and its overall gain. Okay, V01 is the output of op-amp 1 and V02 is the output of op-amp 2. Okay, and now come to this differential part. This is op-amp number 3. Okay, and this op-amp is having output V0 and it has two inputs. The output of op-amp 1 is applied to the inverting terminal of op-amp 3 with resistor R2, and the output of op-amp 2, that is V02, it is also applied at non-inverting terminal of the op-amp 3 with R2, right? I think you have understood the circuit. Now in the next slide we will discuss about the working of this instrumentation amplifier. So in 2 or 3 slides I have also written the configuration. So here you can see that the first stage consists of two op-amps we have seen with inbuilt buffers that make it easy to match impedance matching with the amplifying for the next, that is output stage. V1 and V2 are the input voltages we have already said, and V01 and V02 are the output of the op-amp 1 and op-amp 2 respectively, as far as the buffer circuit is concerned, right? R1, R2, R3 and RG are the four resistors and V out is the output amplified difference of the input signals. We are supposed to derive this expression, and the output gain is controlled by using RG. I have also mentioned this point. Okay, so now come to the uh, working part of this instrumentation amplifier. I think you all know the common concept. When an op-amp is having a negative feedback at its inverting terminal, then we can say that the voltage at this point and at this point will be same. Okay, similarly in case of op-amp 2, the voltage this at this point and at this point will be same. So when these voltages are same, then no current will be flowing in this path. Similarly, no current will be flowing in this path. Okay, and looking to the fundamental concept, whenever an op-amp is having a negative feedback at inverting terminal, then uh, no current would be flowing at both the terminals. So I have marked 0 ampere and 0 ampere similarly at both the op amps. Okay, so if we want to and here uh, we are assuming that this voltage V1 is greater than V2. Okay, and there is a current, only current flowing in this RG, because in this path there is no current, and also in this path there is no current. Okay, now come to this section, that is buffer part. This output voltage, if we want to write the expression of this output voltage with the help of fundamental concept of the normal differential amplifier, then we can write this output voltage is nothing but equal to R3 by R2 divided by the difference of these two voltages. Okay, so V02 minus V1 V01. So this would be our equation number 1. Okay, now our, if we want to write the equation of this current I, and we are assuming that this voltage V1 is more as compared to this V2. So, and the direction of current is always follows high voltage to low voltage path. So this current, the direction of this current would be from V1 to V2, and the expression of this current would be V1 minus V2 divided by RG. So this is our equation number 2. Please take a note of that. We are assuming the output voltage equation of op-amp 3 of the difference circuit, equation number 1, and the current flowing through this RG is equation number 2. Now again come to this part. We are saying that there is no current in this path. Okay, so no current will flow, so we can assume it as open circuit. Also the same case with the op-amp number 2. So the current which is flowing in register RG is basically coming from this side, upper side. Okay, according to the direction of this current. So because these all are connected in series and it is open circuited, so it is considered that the current is flowing from the terminal V01 to R1 and then RG and then again R3, right? Sorry, R1. So this is the current I1 flowing in this total branch. Earlier we have written the expression of this current IG in terms of RG. Now we'll try to write the expression of this current looking to the total branch circuit just by the application of Ohm's law. Okay. So the two inputs of two buffer op-amp draw no current, and hence voltage drop across RG is proportional to the difference between V1 and V2. We have also written the expression. This produces a current that runs entirely through the resistor RG, and voltage produced act as a input to the differential of the output stage. Okay. So the current I through the resistor R1, RG and R1, the R1 just above the RG and this R1 is just below the RG remains the same, because they are connected in series, and ideally the current to the input stage op-amp is 0. Okay, so uh, this current we have already written the current in RG. Okay, and now the total current with respect to the V01 and V02, the voltage difference and total resistance, because all resistance, three resistance are connected in series, and the direct looking to the direction of current from upward to downward, V01 minus V02 would be the voltage difference across that particular branch, and the total resistance of this branch would be R1 plus RG plus R1. Okay, So this I and this I would be same. So if we equate both of these current, we'll be having this expression here. R1 and R1 we have written 2R1. Okay. So uh, if uh, if you look at the first equation, the output equation, we need V02 minus V01. Okay. So looking to this aspect, uh, V01 minus V02 will be equal to 2R1 plus RG. We have placed the value of that current, right? Because this is your V0 R3 upon R2, V02 minus V01. So we have taken negative sign outside. So now the V02 minus V01 will be equal to 1 plus, we have just rearranged the terms, and now this is our third equation. Okay. So V0 output voltage expression would be R3 upon R2, 1 plus 2 R1 upon RJ into V2 minus V1. Okay. So if we want to derive the gain, then our input to the last opamp is nothing but V2 minus V1. So V0 upon V2 minus V1, this is your gain, and the expression of gain would be R3 by R2 multiplied by 1 plus 2 R1 by RG. Here RG plays a very important role, because usually in case of instrumentation amplifier, the value of R1, R2, R3 are kept same and constant, and this RG is external resistance, right? And it is variable in nature. If you vary the resistance RG, then we can control the gain. So this is all about the instrumentation amplifier.